we're going to get in then to solubility equilibrium. Okay, we're going to get into solubility equilibrium. And basically, solubility equilibria is just looking at precipitation reactions. Okay, so solubility is just the opposite of precipitation. Precipitation, as you recall, is when two ions in solution combine to form an insoluble salt, which fall out or precipitate out of solution. Solubility is just the reverse of that. You're putting an insoluble salt into solution and it's dissolving and dissociating to a certain extent. Well, precipitation reactions are really important in a lot of natural and industrial processes. So for example, if you ever get like gallstones, basically that's just calcium oxalate, which is insoluble in your body, and it just keeps building up and forming this little rock that if you ever have to pass one of them, you'll understand what an unnatural event that is. But that's what's occurring in your body. So sometimes, well, a lot of times you don't want precipitation reactions, okay, especially in your body. But other times in industrial processes, they often want precipitation reactions. So your water, so most of your water, I don't know if you have well water, it's not going to be exactly the same, but if you have city water, precipitation reactions is really, really important to you. Because that water is probably coming from streams around the area, which they then dam up. Then they have to clean that water, right? All kinds of animals are doing their business in your water. Companies are dumping toxic chemicals into your water. So that all has to be cleaned up. One of the ways to clean it up, especially to get rid of metals, okay, is to add stuff to the water to precipitate out those metals. So precipitation reaction is really, really important to cleaning up your drinking water. Now they're going to add a bunch of other things too, because not only is it the metals that can be harmful to you, it's a lot of the biologicals. So they're going to treat it with either ozone or chlorine gas, which is going to kill anything biological in it. But again, precipitation is a big part of cleaning up your drinking water. And again, it's used in tons of different other industrial processes. If you're trying to react insoluble salts with other things, well, solubility is going to be an issue because you want as much to dissolve as possible. So we're going to figure out there's ways that we can make things more soluble. We can make more of it dissolve by simply changing the environment that it's in. So that's what we're going to talk about in this part of the chapter. Okay, so I just said that. Let me just read it though real quick. So in this chapter, we're going to examine the solubility of salts that thus far have been labeled insoluble. But again, we're going to find, we're going to quantify exactly how much of that insoluble salt actually dissociates. And we're going to find out for some of them, it is almost nothing at all. For others, a good portion of them will actually dissolve and dissociate. So you need to review your solubility rules. Again, you're going to need them for this section, okay? Okay, so, and again, know your solubility rules, including the exceptions. Okay, so a slightly soluble ionic compound will establish an equilibrium. Okay, we've seen that already. So here's just an example, right? So we have barium sulfate. Now, rule number 4 tells us that most sulfates are insoluble with the exception of silver, mercury, lead sulfates, and barium, strontium, and calcium sulfates are insoluble. So that's why I've got a phase label of a solid. When we throw it in water, it will begin to dissociate into the barium 2+ ion and the sulfate ion. But as soon as these two species start to increase in concentration, they immediately start to react with one another to reform the solid, to recrystallize. So only a little bit of the barium and the sulfate are actually in solution. And so that's why when we go from the molecular equation, where it looks like the undissociated barium sulfate, to the complete ionic equation, we leave it as the undissociated barium sulfate. It's a weak electrolyte. The vast majority of the barium sulfate still in this solid form. Only a minute amount is actually in this ionic form. Okay, so we're going to write an equilibrium constant expression for it. Again, it's going to be the concentration of the products, each raised to the coefficient in the balanced chemical equation, divided by the concentration of the reactants. But this is a heterogeneous reaction, right? Pure solids or liquids don't appear in equilibrium constant expressions. As we've seen with the acids, this really just becomes part of the equilibrium constant itself. And we're going to give it now a new special name. We're going to call it the solubility product constant. So the KSP. Now, in general, the solubility product constant is the equilibrium constant for the solubility equilibrium of a slightly soluble or nearly insoluble, as we're going to find out, ionic compound. The solubility product constant is going to be equal again to the equilibrium concentrations of aqueous ion raised to the power to the number of such ions in the formula of the compound. So again, heterogeneous equilibrium, so the reactant, and it's only ever going to be one reactant, right? There's only going to be 1 mole of the reactant always, which is the insoluble salt. But it doesn't appear again because it's a pure solid. So let's try an example. So let's say we have calcium phosphate. Again, according to the solubility rules, we know that phosphates are generally insoluble with the exception of rule number 1, which states any phosphate with a group 1A metal, so lithium, sodium, potassium, rubidium, cesium, or the polyatomic ion, the ammonium ion, NH4, would be soluble. That is not one of the exceptions, so calcium phosphate is going to be insoluble or slightly soluble. We're going to give it a phase label of S, and when we throw it in water, it's going to be a weak electrolyte, so a double arrow, and it's going to dissociate into the 3 calcium ions with a 2+ charge, and again, 2 phosphate ions with a 3- charge. Again, knowing how to name your compounds is going to make this very easy. Not knowing how to name compounds, this could be a challenge for you. Okay? Okay, so the solubility product constant then is just going to be the concentration of my product. So the calcium raised to the 3rd power, which we see here. And then the phosphate raised to the 2nd power, which we see here. Again, the reactant is a solid, so it's not going to appear in the equilibrium constant expression. So the KSP expression, or solubility product expression, is going to be KSP is equal to the concentration of calcium to the 3rd times the concentration of the phosphate to the 2nd. And again, this is at equilibrium. If this was a Q, our reaction quotient, these would just be the initial concentrations. Okay. So how are we going to find KSPs? How do we determine, experimentally determine KSPs? Well, one way we could do it is fairly simple. We're simply going to dissolve the insoluble salt in water, in a given amount, a known amount of water, okay? And we're going to shake it up and we're going to give it plenty of time to reach equilibrium. Okay, some of these problems, some of these solubilities, it takes a while for the salt to actually reach equilibrium. So again, Yins are doing a lab, and unfortunately it's not in person, so you won't really get to experience that, but you are going to determine the solubility of potassium hydrogen tartarate, which is just cream of tartar. So that salt, potassium hydrogen tartarate, is actually an insoluble salt. It's a potassium salt, I know. Like I said, there are exceptions to even rule number 1, okay? And what you would do is you would dissolve that in a given amount of water, okay? Now the second part you're not going to do in lab, you're going to do something else. Basically then, all you do is then filter off all of the solid, right? So once you filter off all of the solid, you now have a saturated solution of strontium carbonate. No more strontium carbonate will dissolve in the solution. You have the maximum amount of strontium carbonate that you can possibly have in the solution. It's a saturated solution. And then you would simply evaporate off the water, measure the salt on a balance, use the molar mass of the salt, and figure out how many moles you have. Okay, so now we know how many moles of strontium carbonate actually dissolved in 1 liter of water. So our KSP expression is just going to be the concentration of our strontium to the first times the concentration of the carbonate to the first. So there's our KSP expression. Since the concentration is, again, we said that this many moles of strontium carbonate, but there's 1 mole of strontium in 1 mole of strontium carbonate, right? There's only 1 mole of strontium in strontium carbonate. So this 2.37 is also the number of moles of strontium. The same thing is true for the carbonate. If these numbers were different, which I should change it to a different salt, then you'd have to actually, this molar ratio would change, right? If there were 3 carbonates in this salt, this would have to become a 3-to-1 ratio. Okay, so now we know the molarities of both the strontium and the carbonate, so we could just plug that then. And since it's in 1 liter of water, right? Since it's in 1 liter of water, we know these are actually the concentrations, right? So these are also the molarities since it's in 1 liter of water. If this was 2 liters of water, we'd have to divide both of these by 2 liters to get their molar concentrations before we can plug it into this. Okay, so now let's plug in the ice table. So initially we're assuming we have pure water. Again, we don't care about the solid, so there should be no strontium or carbonate in solution. This is actually hard to accomplish here on Earth because there's a lot of carbon dioxide in the air, and the carbon dioxide is absorbed into the water to form the carbonate ion. Okay, so you actually have to take extra precautions when you're doing that, any salts with carbonates. Again, we're going to lose our reactants, but since it's a solid, we don't care, and we're going to gain our products. So plus 1x for the strontium and plus 1x for the carbonate. At equilibrium, we simply add the initial and change. So 0 plus x is x, and 0 plus x is x. Okay, but we know x, right? We know the equilibrium concentration of the carbonate and the equilibrium concentration of the strontium is 2.37 times 10 to the negative 5. So now we can simply plug those values in for the equilibrium concentrations and determine that our KSP for strontium carbonate is 5.6 times 10 to the negative 10. So this is 10 to the negative 10, a really, really, really small K value, which means very, very, very little of the salt actually dissolved and dissociated in solution. Okay, any questions about the KSPs? Okay, let's try another one. So we have a 2-liter sample of saturated lead 2 chloride. Okay, again, that saturated means that we cannot put any more in. That means that that this 7.5 grams all dissolved and dissociated. Okay, so a 2-liter sample of saturated lead 2 chloride solution at 25 degrees Celsius was evaporated to dryness. It was found that 7.95 grams of the salt was recovered. Calculate the KSP for this salt. So this is a more realistic problem of how we would calculate the KSP. So again, we know that when we dissolve the lead 2 chloride in insoluble salt in water, it partially dissociates into the lead 2 plus, and then there's 2 chloride, so the 2 chloride ions. To find the concentration of the lead 2 chloride that actually dissolved, we're going to take the 7.95 grams, divide that by the molar mass of the lead 2 chloride, and then finally divide that by the volume. Okay, that's going to give us the molarity of the lead 2 chloride. This is what we call the molar solubility. This many moles of this salt dissolves per liter. This is what we call the molar solubility. Later on, we're going to talk about the solubility. The solubility is grams per liter. The molar solubility is moles per liter. And to go between the solubility in grams per liter and the molar solubility in moles per liter, all you need is the molar mass of the salt. But most importantly, this molar solubility is X in the ice table. The molar solubility is X in the ice table. It's always going to be X in the ice table. And we call that the molar solubility. Okay, so again, we're going to set up our ice table. Again, we're going to assume we had pure water, so there was no lead-2 ion or the chloride ion in solution. Change, we're going to gain our product, so plus 1x for the lead, plus 2x for the chloride, plus 2x for the chloride. At equilibrium, we're just going to add the initial and change, so this is going to end up being x. So this is going to end up being x, which is going to be equal to our molar solubility that we just calculated on the last slide is 0.0143. And so the equilibrium concentration of the chloride then is going to be 2 times that 0.0143. Now we got to plug that into the equilibrium constant expression, which is going to be the concentration of the lead raised to the first times the concentration of the chloride raised to the second. Okay, now an important thing here, students usually either forget to multiply this by whatever that coefficient is, or they forget to raise it to that power. So be careful with that. Again, make sure you do your homework and you won't make mistakes like that. Okay, so now we're going to plug in our equilibrium concentrations, and that gives us a KSP then of 1.2 times 10 to the negative 5. Any questions about calculating the KSP or what the KSP is? Okay, so the last salt we did was 10 to the negative 10. This is 10 to the negative 5. That means this is 10 to the 5 times more soluble than the strontium carbonate was. But still a very tiny number, still indicating that very little of this actually dissociated and ionized. Okay, so again, the solubility product constants for a whole bunch of different ionic compounds can be found in the tables of chemical data that are posted on Canvas, or of course in the appendix of your TRO text. Okay, next let's calculate the solubility this time. So the solubility is something that non-chemists, so biologists, engineers, this is what they generally use. They'll use the solubility as where a chemist is going to use the KSP or the molar solubility. So you'll need to calculate the solubility, and the solubility is given in units of grams per liter, the molar solubility in moles per liter. So let's calculate the solubility of aluminum hydroxide. So again, most hydroxides are insoluble with the exception of our 6 strong bases. The KSP then of aluminum hydroxide is 1.3 times 10 to the negative 33 for the aluminum hydroxide, okay? Now, we know that the reaction for the aluminum hydroxide is when you throw it in water, it'll dissociate it into the aluminum 3+ ion and then 3 hydroxides. We will set up our ice table. Again, we would assume that we're in pure water, so there's no aluminum, and the self-ionization of the hydroxides is non-important, so we're going to make it 0 again. The chain, we're going to gain our product, so plus 1x for the aluminum and plus 3x for the hydroxide. At equilibrium, we're just going to add them up, so this is going to be x, this is going to be 3x. Our equilibrium constant expression is going to be KSP is equal to the concentration of the aluminum raised to the first times the concentration of the hydroxide raised to the third. Again, noting that X is the molar solubility of aluminum hydroxide. Okay. So we know the KSP, and we know the equilibrium concentrations in terms of X, so we're going to plug them into these values. Now again, this is where you got to watch. This is what students tend to forget. This is 3X, and it is that quantity that is cubed. So it is the 3 is cubed and the X is cubed. So 3 cubed is 27. And then we got X cubed times X, which is X to the 4th. Now we just solve for X, which again is going to be our molar solubility. So I'll divide both sides by 27 and then take the 4th root, okay, or what I like to do is just raise it to the 1/4 instead of dealing with the roots, okay. So I'm going to raise it to the 1/4, and that gives us a molar solubility of 2.6 times 10 to the -9 moles per liter. So that's the molar solubility. To get to the solubility, we're simply going to multiply that number by the molar mass of aluminum hydroxide. Okay. So again, we can see that aluminum hydroxide is not very soluble in water. Very, very, very little of it actually dissolves and dissociates in water. Okay, so now we're going to take the molar solubility. We're going to simply multiply that by the molar mass of aluminum hydroxide. So the solubility then is going to be the molar solubility times the molar mass. The moles cancel. That's going to leave us grams of aluminum hydroxide per liter. And so that gives us a molar solubility then of 2.1 times 10 to the -7 grams will actually dissolve in 1 liter. So almost nothing. But later on, we're going to find a way that we could dissolve every bit of that aluminum hydroxide in water. We're going to convert it from aluminum hydroxide to a complex ion. And all ions are soluble in water, no matter what. Okay, any questions about calculating molar solubilities or solubilities from the KSP value itself? Okay, number 30 from chapter 17 says, use the solubility rules to determine if the following compounds are expected to be soluble or insoluble. And then note what ions form and if the salt dissociates. So again, using the solubility rules, Jada, do you think that magnesium nitrate is soluble or insoluble?
I think it's soluble.
Okay, and if it is soluble, what phase label would we give it?
S. Because nope. the magnesium. I think it's a solid for that one.
Okay, it's actually soluble. Okay, again, the solubility rules that you must know. There are no rules explicitly for magnesium. In fact, they're not even, magnesium isn't even an exception. But there is a rule for salts that contain nitrates, acetates, or perchlorates. And that rule says that any salt that contains the nitrate, acetate, or perchlorate is going to be soluble without exception. And if it is soluble, it's going to get a phase label of aqueous. And only for salts, and of course this is a salt, it's ionic. We have a metal and a polyatomic ion, so it's ionic. It's not an acid. It's not a hydroxide. It's not a metal oxide. It contains another nonmetal other than oxygen. Therefore, it's a salt. And so again, soluble salts are strong electrolytes, which means it's simply going to dissociate into the magnesium 2+ plus the 2 nitrates. Okay. Okay, Katrin, is calcium sulfate, soluble or insoluble?
I think it's insoluble.
Absolutely. And what phase label would it get?
Solid.
Okay. And so according to rule number 4 of your solubility rules, most sulfates are actually soluble, but there are 6 exceptions: the silver, mercury, and lead sulfates. And also, again, those 3 from your strong bases, the calcium, strontium, and barium sulfate would also be insoluble. And so what would I dissociate this into going from the molecular to complete ionic equation, Katrin? What would I dissociate?
Would it just not dissociate?
Well, again, because it's a insoluble salt, that means it's a weak electrolyte. Very little of it actually dissociates. The vast majority of it remains as a solid. And so we're not going to show it as being dissociated. Again, solids, liquids, and gases are at very best weak electrolytes, but we only dissociate strong electrolytes. So again, this is all going back to Chem 110. You must be able to write your molecular complete ionic and net ionic equations for precipitation reactions. I have added a bunch of homework problems from Chem 110 into those sections so that you would have the ability to practice and, again, learn how to do that. Okay. Let's try another then. This is number 34, and it wants us to write the net ionic equation for the dissociation of the following salts and the solubility product expressions for these compounds. So now we do know that this insoluble salt, right? And again, we know it's insoluble because the most carbonates are insoluble. The exception would have been rule number 1, which again would have been those group 1A, so lithium, sodium, potassium, rubidium carbonates and ammonium carbonate, but that is not one of the exceptions. So this would be a solid. Now, it wants us to write the KSP expression, the solubility product constant expression. Well, again, every K, every equilibrium expression is associated to some chemical reaction. So, Jada, what chemical reaction would this be associated with, this KSP value?
Did you say chemical reaction?
Yeah, the chemical reaction, like this. Well, that's not really, like this.
It would be Al2 with...
Okay, Al2, like subscript 2?
2, yeah.
Okay. Again, this is where naming compounds is really, really critically important. From naming compounds, we know that this 2 simply means that there's 2 aluminum. You don't know any polyatomic ion that has aluminum 2, right? We do know polyatomic ion has CO3. So really, there's 2 of these. So there's 2 aluminum. And what would be the charge on that?
2 to the first. So it just be...
I'm sorry, what's the charge on the aluminum?
Can you hear me?
Kinda.
Can you hear me now?
Yep.
Okay. Would it be the charge be negative with the aluminum? Hold on, I can't.
What charge do metals have?
2.
What charge do metals have?
Is it 2?
Nope.
No, then I don't know.
Okay, so the metals are always cations. I mean, there are exceptions, but we're going to assume that they're always cations because they're going to want to get rid of the few valence electrons that they have. So again, we know that if it's group 1A, it's going to lose 1 electron. So these are all going to be +1 group 2b, they have 2 valence electrons, they're going to lose those. So these are all be +2. This is group 3, so aluminum is going to lose 3, it's 3 valence electrons, and it's going to be +3. Now the heavier main group elements, these actually have 2 stable charge states or oxidation states. They can lose all 3 of their valence electrons, so all of these can have a +3, but the gallium, indium, thallium can also lose just a single electron and have +1 as well. So all the other main group elements and all the transition metals can have more than one possible charge state. So that's why we use Roman numerals when we name these compounds, because of those different possible charge states. However, aluminum can only ever be +3. So the aluminum would be 3+. And then we would have the 3 carbonates. And Michael, what charge would the carbonate have?
It would just be 3-.
Pardon me?
3-.
3-. So the
Down,
carbonate,
down.
one of the polyatomic ions that you absolutely must know is 2-. We could also see that in the formula. The 2 would come up, this would be 2-. The 3 would come up, it would be 3+. You have to confirm that. We could always go down, but to go up, you have to confirm. The way to confirm that, well, you know that the 3, well, aluminum has to be +3. And again, we know that carbonate has a 2- charge. This is an insoluble salt. So it would be a weak electrolyte, therefore it would be a double arrow. And so therefore the KSP expression is just going to be the constant, oh, in phase labels, well, all ions are soluble. And so we're just going to write the concentration of the product. So aluminum 3+ raised to the coefficient in a balanced chemical equation times the carbonate, again, raised to the coefficient in a balanced chemical equation. And so there is the equilibrium constant expression, also called the solubility product expression when we're dealing with KSPs. So again, one of the real important take-home messages here is, again, each equilibrium constant has a very specific chemical reaction associated with it. So make sure that if you're trying to compare, so for example, you're trying to compare Q to K, that the Q chemical reaction is the same as the K chemical reaction. Okay. Any questions about that? Let's try another. This time we want to do number 74. It says calculate the KSP of cobalt-2 arsenate, given that the solubility in water is 0.414 milligrams per liter. The solubility, we often give a variable of capital S. So that would be the solubility. The solubility is given in grams per liter, or in this case, milligrams per liter. And then we have the molar solubility, which is just given in moles per liter. Okay, the only difference between the solubility and the molar solubility is you could use the molecular mass to go between the two, the molar mass. Okay, so it wants us to calculate the KSP. So again, we will need the KSP expression. To get the KSP expression, we need the balanced chemical equation to get that. So we have our cobalt 2 arsenate. Again, by telling us that we have a KSP, it's already indicating that it's an insoluble salt, a weak electrolyte. So that means it's going to be a solid and it's going to be in equilibrium with its ions. So again, the cobalt, the name of the compound, cobalt-2, tells us that it's a +2 cobalt. There's 3 of them, and all ions are soluble. So that means that when I brought this up, it was 2+. So that means even if you don't remember what the charge on arsenate is, although you should because you have already memorized that the sulfate, so this is arsenate, right? Whoops, no, we want the phosphate. So there's the phosphate, right? So the phosphate, you know, is PO4 and it's 3 minus. So you should already know that the arsenate is 3 minus. And there's 2 of them, so it'll be a 2. So there is the balanced chemical equation that represents the solubility of the cobalt-2 arsenate. So we are looking for the KSP, and the KSP, again, is just going to be the products over the reactants. So in this case, our products are the cobalt-2 plus raised to the 3rd, and the arsenate raised to the 2nd. The actual original salt's, of course, not going to appear in the equilibrium constant expressions because pure solids and pure liquids do not. They just become part of this constant themselves. Now, if we were looking at this thing, we don't care about the original concentration of the actual insoluble salt because, again, it doesn't appear. We're assuming we're starting with pure water. We're always assuming the reaction is going in the forward direction. So this is going to be plus 3x and plus 2x. So 0 plus 3x is 3x and 0 plus 2x is 2x. Okay, so that means that the KSP expression is then, we could rewrite it. Well, if the cobalt is 3x, that would be 3x cubed. And if the arsenate is 2x, that would be 2x squared. So basically we have 3 cubed, which is 27, so 3 to the 3rd, and then that's going to be times 2 to the 4th, which is just 4. Okay, so that means the number part is 108. Then we have x to the 3rd times x to the 2nd, which is just x to the 5th. So now we have the KSP value in terms of x. So Hannah, how am I going to find x? I have 2 unknowns right now, or do I actually, can I find one of them? I mean, in the end, I'm looking for the KSP.
You can find it using the solubility.
Okay, how?
The molar mass relates the KSP to solubility. Right?
Okay, so I have 0.414, and this is milligrams, and this would be our cobalt-2 arsenate. Okay, and that's per liter. And so you're talking to molar mass, so that means I'm going to have to get this to grams.
Mm-hmm.
So there's 1,000 milligrams in a gram. And then you're saying I have to, what, multiply or divide by the molar mass?
Divide by it.
Yeah, right. We're going to divide by the molar mass. So just calculate the molar mass. So 1 mole is going to be 454.638 grams. The grams are going to cancel. Okay, now what?
That in itself should be the KSP.
Nope,
No?
not KSP. So if this was the solubility, what would you call what we have right now? If this value here alone was the solubility, what would you call this quantity?
The molar solubility?
Yeah, right. It's just moles per liter now. So this is just the molar solubility. Let's get rid of that. So that's not the KSP. So as you recall from lecture, the molar solubility is X in the ICE table. The molar solubility is X. So that's basically the moles per liter of this stuff that'll actually dissolve at equilibrium. So that's X. So we just simply plug this value in and we get 9.1061 times 10 to the negative 7 molar. We have 3 sig figs, that's exact is 6, so there's 3 sig figs. And now to get the KSP, all we got to do is plug that value in. So 108 times 9.16, no, 1061 times 10 to the negative 7. And of course, that is to the 5th. Plug that into your calculator. That's going to give you 6.7623 times 10 to the negative 29. This would be exact, and this would be 3, so that's 3. And so your final answer then would be 6.67 times 10 to the negative 29. Any questions about that? So again, the really important thing here to know is, again, for solubility, the molar solubility is just X in your ICE table. The solubility is given in grams per liter, and the molar solubility is given in moles per liter. Okay, any questions about that guy? Okay.
Wait, I had a quick question.
Yep.
Just going back to the net ionic equation.
Yep.
For the arsenate, why is it given a phase label of aqueous? It's just
Because all ions are aqueous.
oh, okay.
Okay, again, that's really important. All ions are always aqueous. Okay, let's try number 39. It says calculate the molar solubility of magnesium carbonate from the equilibrium constant. So this basically just wants us to go backwards. It wants us to go from the equilibrium constant to the molar solubility. So first we got to write the, if we want to use the KSP to do that, right? So that's KSP is what that means. We got to have the proper chemical equation for it. So again, we have magnesium carbonate, magnesium, and there's the carbonate. This is a +2, right? It's a group 2 main group metal. And the carbonate, again, of course, I know you've all memorized the polyatomic ions that you're absolutely supposed to know. And so the carbonate is a -2. So we have a +2 and a -2. So that gives us magnesium carbonate. And we already know that carbonates are generally insoluble with the exception of rule number 1. So we know that this thing is a solid. And there's no space there. This is magnesium carbonate, 1 molecule. Again, it is a weak electrolyte since it's a solid, an insoluble salt, and it's going to dissociate into the magnesium 2+ and the carbonate CO3 2- aqueous. And so the KSP expression then, again, is just going to be the concentration of the products, each raised to the coefficient in the balanced chemical equation, divided by the reactants, but in this case, the reactants is solid, and pure solids and liquids don't appear in the equilibrium constant expression. Our ice table then, again, whenever we have weak electrolytes, I better see an ice table. You can't solve the problems without them, okay? I don't care how simple the ice table is. I want to see your work. I want to see the ice table. So again, we're going to assume that we dissolved the magnesium carbonate in pure water, so there was no magnesium or carbonate in the solution to begin with. The change, again, we're always assuming the reaction goes in a forward direction, so we're going to gain 1 of the magnesium, so plus X, and 1 of the carbonate, so plus X for it. At equilibrium, we simply add up the initial and change. That's 0 plus X for both. Now, again, we're looking for the molar solubility. So what are we looking for?
X.
X, right? The molar solubility is just X. So we're looking for X. So this is equal to X. So I'm going to look up the KSP. Okay, so I'm just going to look in the tables of chemical data, and I find that the KSP is 6.82 times 10 to the negative 6. Then this is X, and this is X, so that's going to end up being X squared.
Wait, I have a quick question. Where you got that KSP? Like, where exactly?
Tables of chemical data.
Yeah, but like, is there like a specific element you have to look it up on?
They're in alphabetical order. So
Okay.
if it's cobalt, if it is it's magnesium. No, what the hell is going on here? Yeah, okay, it's magnesium carbonate. They're in alphabetical order. So I look up, let's see, magnesium carbonate.
Okay.
6.82 times 10 to the negative 6.
Okay.
So they're listed in alphabetical order according to their name. Again, another reason you must know how to name compounds. Okay, so again, we're just looking for X. So we're simply going to take the square root of both sides. And so X then is simply going to be equal to, make sure I'm doing the right one. Here we go. Okay, so X is going to be equal to 0.0026115. Let's see, so 3 sig figs, since this is 3 sig figs. So, and again, remember, this is molarity, so it is moles per liter. So X, the molar solubility, is going to be equal to 2.61 times 10 to the negative 3, and then moles per liter. So you could write it as molar, or you could write it as moles per liter. Then if we wanted the solubility, we'd simply multiply this by the molar mass of the magnesium carbonate. So any questions with that? Okay, let's try another. It says, given that the solubility of iron 2 fluoride in water is 0.791 grams per liter, so again, it's giving us the solubility. What is the solubility of iron 2 fluoride in a 0.5 molar iron 2 nitrate solution? Now again, you got to recognize there is only one relevant chemical reaction here. And again, it all comes down to being able to understand how to write the correct chemical reaction for things. So basically, we have 2 things going on here. We have the iron 2 fluoride. Now, it's telling us that this has a solubility, which means it's a weak electrolyte. It's an insoluble salt if it has a limited solubility. So that means this is a solid, which means it's going to be in equilibrium with its dissociated ions. And the 2 fluoride. So there's the reaction that we're talking about for the iron 2 fluoride. But it's saying it's already in a solution of iron 2 nitrate. Well, for the iron 2 nitrate, well, I know according to my solubility rules that nitrates are soluble salts, therefore a strong electrolyte. So there's no equilibrium going on here. It just associates into the iron 2 plus the 2 nitrate ions. And it wants to know what is the solubility of the iron 2 fluoride. So it's also saying, hey, look, we're looking for the solubility of the iron 2 fluoride. And as we've seen, we're going to have to get that solubility from X, the molar solubility, which means we're going to need the KSP expression, which is just going to be the concentration of the iron 2 plus times the concentration of the fluoride squared. Right? Because again, we know that the molar solubility is X, and we can get to the solubility by simply determining the X value and then using the molar mass. Okay, so how am I going to go about solving this problem then? So first, I tried to look for the KSP of the iron 2 fluoride. I couldn't find it. It wasn't in the tables. So what am I going to do?
Can you start with getting the molarity of the iron 2 fluoride by using the molar mass?
So you want me to get the, say that again?
The concentration, get into moles per liter.
What exactly, what value, what number are you talking about here?
0.791 grams per liter of the iron fluoride.
Okay, so you want me to convert this from grams to liter to moles per liter?
Yes.
Okay. So I'm going to do that down here. So I have 0.791 grams of the iron 2 fluoride per liter of solution. And we're going to divide this then by the molar mass of the iron 2 fluoride. So there's 93.842 grams per mole. Again, this is for the iron 2 fluoride, so the grams cancel. We got moles per liter. Okay, how did that help me?
Oh, I forgot to mention setting up an ice table.
Okay.
Which would be the initial that one.
Okay.
Oh wait, but it's a solid. But wouldn't that be X for when you do solve?
Okay. Yes, this would be X. Yep.
Yeah.
Right?
So
this is X, the molar solubility.
Sorry, I'm like doing this over here, so I'm jumping around. But
why are you going in this direction though? It's important to know where you're going.
So in the ice table, under the iron, it would be plus X, and then the fluoride would be plus 2X.
Okay, so what is my initial concentrations?
The initial, well, that's a solid, so that we don't.
Okay.
And then we're not given the iron and the fluoride, I think.
I'm just trying to figure out what route you're taking here. Do you see the big picture? We are trying to find the solubility of the iron 2 fluoride in a solution that contains iron 2 nitrate.
Okay. Now I'm second guessing this.
Well, what were you doing? What were you going to do next?
Well, I was gonna set up the ice table,
Okay.
and that would end up being like x plus 2x, so 2x cubed.
So you're saying the initial concentration of both of these are zeros?
Yes. Oh, because it dissociates, yeah.
Okay.
Because we're not left with
But we're talking about, I'm just going to rewrite this real quick. I just don't, you're not conveying to me yet that you see the big picture. So we're looking for the solubility of the iron 2 fluoride in a solution that already contains 0.5 molar iron 2 nitrate. Now we've established that in that solution, the iron 2 nitrate is a strong electrolyte and completely 100% dissociated into the iron and the nitrate. So if this was originally 0.5 molar, what's going to be the concentration of iron at this point?
if it dissociates completely, wouldn't it just be 0?
So
Okay.
this just disappears altogether?
No.
It goes from 0.5 to 0?
Well, we're not given the value, so I guess it'd just be x.
Well, it does tell you. It tells you that the iron 2 nitrate was 0.5 molar. And it completely dissociates into iron and nitrate.
Okay, so then wouldn't the nitrate be 0 and then the iron be 0.50?
So 0.5, right?
Yeah, 0.5.
Okay, and then what was the nitrate?
It'd be 0 because it dissociates completely.
But there was 0.5 of these guys.
It'd just be x.
And then there was 2 of the nitrates.
So it'd be 2x.
It would be 2 times the 0.5,
Oh, okay, because 0.5 is x.
right? It's double that, right? So this would actually be 1 molar. Okay. So in other words, so this is an arrow. So we already know these concentrations. How does that help me determine the solubility of the iron 2 fluoride? What am I going to have to do to find the solubility of iron 2 fluoride in the solution that already contains this? Anybody?
Would you find the equilibrium of Fe2+ and then plug that into the other ice table?
Is there an equilibrium here?
Oh no.
Why not?
Because there's no given value to solve for equilibrium. I don't think.
Well, it's a strong electrolyte. Again, because you know your solubility rules, you know that the nitrates are going to be soluble, which means they're strong electrolytes, which means they completely dissociate. So there's no equilibrium here. We've established that this completely dissociated into this. But how does that help me down here again? Right? This is a weak electrolyte. So this is where the solubility is going to come from, the solubility of the iron 2 fluoride. So basically for this part of the problem where we're looking at these, we dissolved the iron 2 fluoride in a solution that already contained the 0.5 molar iron 2 nitrate. If all we're concerned with is the KSP of this iron 2 fluoride, we would set up an ice table. The solid is irrelevant because it doesn't appear in the KSP expression. Is the iron 0?
Is that the 0.5 molar?
Yeah,
Yeah.
right? It already has 0.5 molar iron in the solution. What about the fluoride?
Do we not know the fluoride?
Did they tell you that they added any?
No,
So why would you assume that there was any in it?
we
Right.
wouldn't. We shouldn't.
So we would be, yeah, we would assume, you know, you don't make assumptions like that, right? We assume it was pure water and all they had was this. Okay, what about the nitrate? What effect does it have?
None.
None. It doesn't appear in this reaction. Again, it's a conjugate base of a strong acid, so it's not going to hydrolyze. It's not going to change the pH. Right? And the pH oftentimes, as we've already seen, can affect the solubility. But since it's not changing the pH, it's not going to affect the solubility. Okay, so now the change, well, again, we're going to gain, so it's going to be plus 1x for this and plus 2x for this. At equilibrium, we just add the two. Now the KSP expression was given as this. So that means the KSP would be equal to the iron. And then the fluoride squared. So if we're looking for the solubility, what are we solving for here?
X.
We're solving for X, right? Because we know that we can take X and eventually go to the solubility from that value, right? By using the molar mass. So we would need the molar mass. We would multiply it in this case by the molar mass, and that's where our solubility comes from, right? It'd be X times, so this would be X times the molar mass. So what about KSP? So again, this is the big picture, right? So this is what I'm trying to solve, but I can't find the KSP in the tables. So I think this is where Leah was going, was that this is the solubility in pure water. So like we did before, when we had the solubility, we were able to calculate the KSP. And that's, again, exactly what we're going to do here, right? So in pure water, that's what we did here. This is in pure water, because that's what it told us. So that's the X. So in this particular case, if it was pure water, there was no iron or fluoride in pure water. Again, this would be plus X and then plus 2X. So X and 2X. So to calculate the KSP then, that'd be X times the 2X squared. 2 squared is 4. And then we have X squared times X, which is X to the third. So if we plug this in and we get our X value, which would be 0.008429, and that'll be to 3 sig figs. Okay. And so this is molar. Well, we know that that's X has units of molarity. So KSP then is going to be 4 times this 0.008429 cubed. And so the KSP then has a value of 2.395 times 10 to the negative 6th. 3 sig figs. Any questions about that so far? Okay, so now that we've determined the KSP, we can plug it into this equation. So now we come over here and we say 2.395 times 10 to the negative 6th is equal to this whole thing over here. I am going to make the assumption. Now, in the solutions manual too, I used Y's for all of these, just not to confuse it with this part over here. So I just used Y's. Now, again, I'm going to make the assumption that X is so small compared to 0.5 that that can be ignored. We can always come back and check that assumption later, but we're going to assume that that is so small. So that's just going to make it easier for us to solve.
Why did you do that though? Like,
I'm sorry.
what allows you to like do that?
Well, we're going to check it. Well, nothing
Right.
allows us to do that. We got to go back and check to make sure that that was an okay move, just like we've always done before, right? So now basically what I have is I have, so 2 squared is 4. So the X is gone, right? We're assuming that we could ignore this. So basically then we have the 4. So I have my 0.5, I have 4, and then I have X squared. So X squared is going to be equal to then the 2.395 times 10 to the minus 6 over 0.54, okay? And then to get rid of the square, we're going to take the square root of both sides. And so X then would be equal to 0.0010944. Now we have to go back and check. Okay, so this is where we're now going to have to go back and check. And so we take 0.50 and we're going to subtract 0.0010944. Okay, that is going to give me, oh, this is plus, I'm sorry, plus. So that is going to give me 0.50.
Can you move the paper up?
Oh, I'm sorry.
Thank you.
109. Well, the 2 sig figs, right? The 2 sig figs that it was, that is 0.50. So our assumption is good. This was good. We checked it and it's good to go. So now I know X, which is our molar solubility, right? This is moles per liter or molar. And I want the solubility, and we already said, well, to get the solubility, we're just going to take X times the molar mass. X we just determined is 0.0010944 moles of the iron 2 fluoride per liter of solution. So to get the solubility, we just got to convert those moles to grams. So we're going to multiply by the molar mass, which we said was 93.842 grams per mole. The moles cancel, and that leaves us with grams of iron 2 fluoride per liter, which is going to be 0.1027. Let's see, this was at, so this is now at 2 sig figs. So this is 2 sig figs. This is grams per liter. So 0.10 grams of iron 2 fluoride per liter of water. So there is our solubility. Any questions about that?